So I will talk about this recent work of me and Suguru Tamaki about called dequantizing short-path quantum algorithms. And so if you have any questions about this during the talk, please feel free to ask them during even early stages of the talk. So I have only about 20 or 22 slides, so we have enough time for questions. Start with a brief background. I think most of you know that it's some kind of background about the quantum computing and the quantum algorithms. So the main focus of this talk and the background for this research is the concept of a quantum advantage. Okay, so here you see a brief partial description of the achievements in terms of construction of quantum computers. So we started with a small quantum computer, 5 qubit, 10 years ago. Now we have around 1,000 qubits. Of course, to do tasks like integer factoring, you will need error correction. So you need a huge amount of qubit. It's very far from what we can do so far. But it's known that even with a small scale quantum computer that we have currently, we can solve some problems faster than any classical computers. So a very famous example is a well-known quantum supremacy claim by the Google group in 2019. So what they have done, they have considered the task of computing the output of a random quantum circuit working on the 53 qubits. So if we have a quantum computer of 53 qubits, you can do it almost natively, and they have given evidences that it's hard to do classically. Okay, so this gives you some examples of tasks that can be done efficiently on a small-scale quantum computer, but are hard to solve even with classical supercomputers. And there have been a lot of similar results obtained in the last 5 or 6 years. But the point is that the task considered here is artificial. Okay, so all the other what is most of the recent paper showing this kind of similar quantum advantage also consider artificial problems. And what we really would like to understand is how to get quantum advantage for natural or at least interesting problems. This is really what we want to build a quantum computer for, not to solve artificial tasks, but to get a speed up for natural and important or at least interesting problems. And of course, we do have Grover search. Okay, so we probably all know Grover search. Grover search shows that for a generic search problem without any additional structure, you can find a solution in square root n calls to a black box, where n is the number of elements that of the whole search space, while classically, if there is no structure, you will need a linear amount of calls. So this gives you a quadratic speedup. And it's extremely useful in the sense that the search is a very important primitive in algorithms. So with this unique quantum algorithm, you can already get thousands of quantum algorithms by applying this to many known classical algorithms. So it's a very universal and very practical techniques giving speed up for many natural problems. But of course, the main issue here is that it gives you only a quadratic speedup at best. And it's completely unclear at this point if this is enough to observe in practice some speedup. Indeed, it's unclear if a quantum algorithm working in time square root n will be faster than a classical algorithm working in time n. Why? Because we are talking about asymptotic complexity here, and they are in hidden constant here in these notations. And especially in the quantum case, a hidden constant can be very huge. because it will represent the cost of implementing one basic quantum gate. And this can be much more, much higher than the cost of implementing one basic classical operation. Okay, so in order to understand whether this Grover algorithm leads to a speed up in practice, you really need to get a better understanding of the architecture of quantum computers, and we don't have this currently. Okay. What's much more interesting is super-quadratic advantages, again, for natural problems. And we know a few quantum algorithms achieving such kind of speedups. For example, finding hidden structure in abelian groups. This is essentially Shor algorithms. This can be extended to solving instance of the hidden subgroup problem and so on. We also know some exponential advantage for phase estimation, for problems like correlation, even for quantum walks, for walks in some specific classes of graphs. Also, we have HHL that gives some speedups, sometimes exponential for problems in linear algebra. But the point is that many of those results have few applications with rigorous end-to-end quantum advantage. Okay, so for example, correlation is a problem about query complexity. Okay, it really assumes that you can access a function only as an oracle. Okay, HHL really makes strong assumption on the way the input is given and the output is computed by the algorithm. You need to have some quantum state, the input as a quantum state, and the output will be typically also a quantum state. So if you really want to find natural problem with a rigorous end-to-end quantum advantage, essentially the two main known examples are still integer factoring and then some problems related to simulating quantum mechanics, like estimating the ground energy of quantum systems. Okay? And there is another proposal to get some possibly super-quadratic speedup, which is the quantum adiabatic algorithms. It was originally proposed in 2000 by these four guys. Okay, and I will try in the next few slides to give some very rough description of what quantum adiabatic algorithm are, but the point is that it's not so important for the following of the talk, because the conclusion of this talk will be that we don't really need that, at least for the problem we are discussing. We can dequantize everything and design classical algorithms. So I'm mostly explaining the concept of a quantum adiabatic algorithm to give some kind of a background and explain this line of study. Okay? So the main idea of quantum adiabatic algorithm is to prepare a quantum system in a ground state of a fairly simple Hamiltonian H0 and to let it slowly evolve into another Hamiltonian with ground states encode the solution of the problem we want to solve, typically a classical optimization problem like 3-SAT or traveling salesman problem. Okay. Of the whole process as described by an Hamiltonian HS. S represents the time from S equals 0 to S equals 1. So initially, for S equals 0, you have the Hamiltonian H0. This is the initial Hamiltonian, which is an Hamiltonian with very easy ground states, very easy to construct. And finally, you will have S equals 1. We'll have the Hamiltonian H1, which encodes the problems that you want to solve. And of course, its ground state will encode the solution of the problem you want to solve. So very something hard to compute. And you make the transition from S equals 0 up to S equals 1. And we have some theorem called sometimes the adiabatic theorem that say that if the evolution is sufficiently slow, the system remains in the ground state throughout the evolution. So you start with a system in the ground state of H0, which is very easy to obtain. And if you make the evolution, the time evolution slow enough, then at the end you will be in the ground state of H1. And this ground state represents the solution of your optimization problem. And everything is, of course, this notion of sufficiently slow. So this means that mathematically you can show that you need to have an evolution which is relative to the inverse square of the minimum spectral gap. So the important thing is the spectral gap. If the spectral gap is very small, then you will need a lot of time. A lot of, yes, you will need to do the evolution very, very slowly. So finally, you will need a lot of time. If this spectral gap is large enough, then it can be much more fast. Okay, so concretely, for the problems we'll consider in this talk, we can take the following two Hamiltonians. So in this talk, we consider a minimization problem. Okay, so we want to minimize a function. The function is defined over a set of strings and has real values. So a concrete example is to minimize the number of unsatisfiable clauses of a strict-sat formula. Of course, there is an equivalent version, which is to maximize the number of satisfiable clauses. But in this talk, I describe everything as a minimization problem. Okay. Okay. And in this case, so H1, which encodes the minimization problem, is simply a diagonal matrix, where each entry of the diagonal represents G evaluated at one of the strings. Okay, so you have 2 to the n strings, so this gives you a 2 to the n by 2 to the n diagonal matrix. And the eigenvalues are precisely the values in the diagonal, and the ground state, and the smallest eigenvalue, is precisely the eigenvalue corresponding to the solution, Z star. And the ground state will be precisely this. Okay, it's very simple because it's diagonal. And H0 is typically taken as this Hamiltonian, which calls the transverse field operator. And it's defined like this, but definition is not so important. The point is that the ground state is simply this state, ket plus tensor n time by itself. So you see that if you apply H0 to it, what you get is the same vector multiplied by minus n. So the eigenvalue corresponding eigenvalue is minus n, and it is the smallest eigenvalue. The point is that you can create the ground state here extremely easily, because the ground state is almost trivial. Okay, so we do have again this adiabatic theorem that says that if the evolution is sufficiently slow, then you will get a solution of your optimization problem. And so you really need to understand this spectral gap. And you need to prove a lower bound on this spectral gap. But you do need to prove a lower bound on the spectral gap that will hold through the entire evolution. That is a lower bound that is true for all the values of S from 0 to 1. And this is the main challenge. Usually you can prove things, say, when S is very small or S is very large, but we don't know how to prove nice bounds for all the values of S. And that's why this concept of quantum adiabatic algorithm has not been very successful so far to prove a rigorous bound of quantum algorithm for optimization problems.
Sorry, can I ask a quick question here?
Sure.
Is there some kind of hardness result that is known, maybe saying that if one is able to generically find the lowest energy gap, then maybe one can solve some hard problem. Do we have any kind of understanding of that nature here?
Yes, so I would guess that it is at least just NP complete in general. So I'm not familiar precisely with the complexity of this problem, but I will guess that it is very hard. I mean, if you have a general Hamiltonian, you know, computing the ground energy and all those things are QMA hard. Here, the Hamiltonian is much easier because you know that H1 is diagonal, but I'm pretty sure that we can show that it is at least NP hard.
I see. Okay.
Yeah,
Thank you.
sorry to interrupt. Yeah, you can show that it is NP hard because H1 can encode the Hamiltonian of an NP hard problem. So where if you find the ground state of H1, you would be essentially solving the NP hard problem. So yeah, it's at least NP hard.
Yeah, at least NP hard, and I think it's probably much. Well, I don't know, but I won't be surprised if it is even harder than that. Yes, but at least NP hard.
So sorry, I think I maybe didn't fully understand the connections. I was meaning to ask whether you can find a spectral gap, like find a formula for the spectral gap or the lowest, like find the smallest gap that occurs as you change S. I was asking if that problem is NP hard. Is that what you meant? Ground state I understand, but are they related or?
Yes, it's a good thing. So they are not exactly the same because the spectral gap is a gap between the smallest and the second smallest eigenvalue. But I'm pretty sure the complexity should be very similar.
I see.
Because if you put an artificially a dummy state at a very, very low level that you know, then essentially the spectral gap becomes the ground energy of very close. Yes.
Okay, thank you. Sorry for the interruption.
Yeah, thanks a lot for the question. So any other questions?
No, just a comment regarding like a follow-up regarding Atul's question. So if we imagine that H0 is the one-dimensional projector state, so it's like plus tensor n ket plus tensor n bra, and H1 is say some NP hard Hamiltonian. In that case, you can show that the minimum gap over S, if you vary S from 0 to 1, the minimum gap is exponentially small. So so it's like unstructured search. So you cannot get so in that case the gap is exponentially low and you can get like a quadratic advantage at most.
Okay. Thank you. Any other comment questions? Okay, so this was this general framework of a quantum adiabatic algorithm. So now what has been proposed in the series of paper called introducing the concept of what's called the short path quantum algorithm, which is what we will dequantize in this work, is the following. So you have the same idea, the same kind of Hamiltonian. So H0 easy to create, especially the ground state is easy to compute. H1 is what we want to solve. I mean, it's an Hamiltonian encoding the solution of your optimization problem. But the basic idea here is to not evolve the system from S equals 0 to S equals 1, but to make it evolve from S equals 0 to S equals t for some small t. Say t equals 0.01 or something like that. And then jumping to the end via a measurement. Okay, so you evolve it a little bit, and then you measure your state. And you see if you have a solution. Okay. The good thing is that it avoids the need to control a spectral gap through the whole evolution. You only need to control a spectral gap from S equals 0 to S equals t. Okay, small t. It's a good thing. And another way of interpreting this algorithm without using this notion of adiabatic algorithm is the following. So you will apply phase estimation to HT. Okay, so T is again a small value. So you want to do the evolution from s equals 0 to s equals t. T is a small value, say 0.01. So you want to apply phase estimation to HT. In order to do it, phase estimation assumes that you have a quantum state, which is usually, well, ideally, it's close to the ground state, but not necessarily. And this time you apply phase estimation with this psi 0 as a guiding state. Okay, so psi 0 is the ground state of H0. Okay, and your goal is to construct the ground state psi t, the ground state of HT. Okay, and this will work well, of course, if H0 is small, H0 is close, psi 0 is close to psi t. Okay, so in particular, if the inner product is not too small. And an external case is when t is extremely close to 0. When t is equal to 0, of course, ht is equal to h0, so psi t is equal to psi 0. So, of course, the overlap is 1, the inner product is 1. When t will be very, very small, but non-zero, then we can expect that this inner product will still not be too small. Okay, so phase estimation is expected at least to succeed with a non-trivial probability. The first step. Okay, you apply phase estimation using as ground state psi 0 that we know. We know psi 0. And the second thing, we measure psi t in the computational basis, and we simply output the result. Okay, this corresponds to the jumping to the end part of the description I gave in the first part of the slide. And this will work well if this inner product is not too small. So for example, when t is close to 1. If t is equal to 1, then this inner product will be 1, because the ground state of H1 is precisely this optimal assignment, Z star. Okay? So we have this approach. And Hastings, in a series of papers, show that under several conditions, these two requirements can be simultaneously satisfied. So there is a value of t such that this thing is not too small and this thing is not too small. And if you take this value of t under some condition, you get a non-trivial algorithm for solving optimization problems. Okay, and I will give more details about these assumptions in the next slide. But are there any questions about this description of the short path quantum algorithm?
Just to quickly check, so Z star was the solution, right? If I remember correctly.
Yes. So I will go back to yes, important things. I will go back here. So, yes. So we consider a minimization problem, and the Z star is a solution.
Right.
So you can think that the solution is unique. So it's a unique solution. If you.
I see. Okay.
Any other questions? Okay, good. So now I will discuss the results first proved by Hastings in 2018 and 19, and then revisited in this paper published in STOC 2023, where they, in some sense, reinterpreted the result by Hastings in more using a terminology closer to the terminology used by people doing theoretical computer science. Okay. So the optimization problem considered is called MAX-k-CSPs. Okay, so the name is complicated, but what's done here is very easy. So the goal is to minimize the number of unsatisfiable clauses of a Boolean formula in which each clause is a parity of exactly k variables. This is an important point. Each clause is a parity of exactly k variables. So for example, for k equals 3 and you have n equals 5, so 5 variables, and here I have 4 clauses. Each clause is a parity of exactly k variables. Okay, and I want to minimize the number of unsatisfiable clauses. I want to find the assignment that minimize the number of unsatisfiable clauses. And I will call UZ the number of unsatisfiable clauses of the assignment Z, and U min the minimum. Okay, so I want to find U min. And the low energy density condition is the following condition. Informally, it says that there are few assignments with low energy. It says that for some gamma and mu, the number of assignments such that the number of unsatisfiable clauses is smaller than this, is smaller than 2 gamma n. So I will show you a graph. It's much easier to understand here. So it's a graph showing, so the vertical axis is, is the number of unsatisfiable clauses, and the horizontal axis represents all the 2 to the n assignments. Okay, so each assignment at different value of uz, and the minimum value is achieved here. Okay, and this low energy density condition say that if you look at the number of assignments with value uz smaller than this threshold, smaller than this line, then you have only a few number of them. Okay, smaller than 2 to the gamma. So you can think of gamma and mu being constant. Okay, say mu equals 0.01 and gamma say 0.99 or something like that. Okay, and this condition says that there exists such constant gamma mu such that this is true. And Hastings have shown that there is a quantum algorithm which, for any instance of this problem satisfying this star condition, produce an optimal solution with high probability in this time. Okay, C is this value. So the point is that when k is a constant, which is the case, usually we take k equals 3 or a small value, and if gamma and mu are constant, which is the case in this low energy density condition, then C is also a constant. So you do get something which is faster than Grover algorithm. Okay, and now in the next slide, I will explain how to remove this condition, how to remove the low energy density condition. Okay, but is there any question about this result, the first result of the series of paper on the short path quantum algorithm?
Oh, okay, so maybe just to make sure I'm not missing anything obvious, when they use the word super Grover, I don't suppose we have a corresponding classical bound rate for the same problem, in the sense that
the conclusion of this talk and this work is that actually there is no super Grover speedup because we can do something fairly efficient classically. But at the time the paper was written, there was no non-trivial strategy for that problem. So classically, it was expected to be 2 to the n or something like that. So compared to 2 to the n, the trivial classical strategy, this is more than quadratic.
Right. Right. Okay. Thank you.
Any other questions? Okay, so now I will move to the next one. So I will discuss the main contribution of this more recent paper, which is removing this condition. This condition is a bit annoying because it says something extremely interesting, but for instances satisfying a condition. And we're not really sure if there exist such interesting cases satisfying this condition. So we would like to remove such kind of condition, and it is actually possible. And the problem for which it's possible, it's actually even broader than the problem considered in the previous slide. This time, we don't really need to restrict clauses to parity. You can have any predicate on k variables. Okay, so it's even more general than the problem we discussed in the previous slide. And here is the main result that I call the theorem B. Theorem A was a theorem in the previous slide. There is a quantum algorithm that works for any instance of this problem, very general problem, and that produces an optimal solution with high probability in this time. Okay, and so the point here is that you don't have any condition anymore. You don't have to assume the star condition as in the previous slide. It works for any possible instance. Okay. The bad thing now is that, or it's not so bad, but the weakness now is that C depends on a few other parameters. Before that, C was very easy to write. Now it involves two new parameters. The first one, D, is the regularity of the instance. Okay. So you have D equal 1. Variable is involved in the same number of clauses. Okay. And if this is not the case, if there is a lot of irregularities, say one variable involved on many clauses, then D will be much smaller. Okay. And the second parameter, which is even more important, is delta, which is a fraction of clauses satisfied by the optimal assignment. Okay, so you will have delta equal 1 if the optimal assignment satisfies all the clauses. And in spirit, you will have delta equals 0 if the optimal assignment satisfies no clause. But it's not exactly this, because you can observe, for example, for MAX-k sat, if MAX-k sat, so MAX-k sat in the case where each clause is of this form, the OR of 3 variables, it's easy to check that if you take a random assignment, you can satisfy each clause with probability 7/8, which means that a random assignment satisfies a fraction 7/8 of the clauses. So this also means that it's very easy to find an assignment satisfying a fraction 7/8 of the clauses. So instead of having no clause here, it should be this. We set delta equal to 0 if the optimal assignment satisfies the same number of clauses as a random assignment, the trivial, some kind of trivial assignments. Okay. Okay, so we have this.
Can I quickly ask? Yeah. So sorry for the interruption. So, but what is can capital D depend on little n?
Sorry, can you repeat your question? The D here?
Sorry, I was just asking about the regularity of the instance. Yes. So can capital D, like you said, it's 1 if each variable is involved in the same number of clauses.
Yes.
But on the other extreme, how big can capital D be? Does it depend on little n?
Yes. So D will be something. Yes. So B will. Yeah. I mean, it's larger than 1, so it can be up to something like n or something like that.
Okay, but it can't be like exponential or something. Okay.
No, it cannot be. No, it cannot be exponential. Yes, it's
okay.
At most a polynomial. Yeah.
Okay, thanks.
Yes. But so, even if the average degree is constant, then D will be usually very close to 1. So it's not a very strong condition to assume that D is close to 1. And so to summarize the conclusions of this theorem, the implication of this theorem, so it shows that when D is upper bounded by 1, so when the instance is, say, mildly irregular, and when delta is a big omega of 1, then you do get C constant. Okay? And then you do get a super-quadratic speedup over the best non-classical algorithm, because the best non-classical algorithm were, again, trivial, so complexity to the n. And the good thing about this second version, of course, the constant C is a little bit more complicated because it depends on 2 parameters, but you don't have any density condition required for the result to hold. So any questions about this version? So from perspective of computer scientists, the fact that D is small is, I think it's okay. In most cases, all those problems are hard, even for mildly regular instances. In many practical situations, this is really the most typical case. So it's not having D upper bounded by 1 or upper bounded by a constant. It's not a strong assumption. And the second assumption, delta big O of 1, is a little bit stronger, but it still occurs in many concrete situations. So the regime for which you get a super-Grover, a super-quadratic speedup is still fairly interesting. Okay. And I can briefly explain how they prove this. They essentially prove this by showing that when these 2 conditions are satisfied, then the low energy density condition is always satisfied. So they are not assuming this low energy density condition, but they show that the condition on the degree on the parameter D here and the condition on the parameter delta imply that low energy density condition. Okay, and you can see it here. So when delta is a big O of 1, what does it mean? This means that there is a big gap between the average number of unsatisfiable clauses and the minimal number. So you have a big gap here. And then you obtain that the number of assignments with low value here, the number here, assignments in red, will be small. You can get it easily from standard concentration bounds and using some more precisely the Mach-Diamine inequality. Okay, so I will not explain precisely how you do this, but this follows really from these 2 conditions, that delta is large enough and D is small enough in order to be able to apply this concentration bonds. Okay, any questions about this? Okay, so now I can explain our results. Okay, remember this is theorem B. Okay, so what we show is that there exists a classical algorithm that for exactly the same kind of instances produce the same thing, an optimal solution, or again with high probability. And the time complexity is this. Okay, where C2 is a new value, which is this. And the point is that C2 is always larger than CB. Why? Because if you look at the constant, you have a greater constant here. And then the difference is a power 2 instead of power 3. But this delta is smaller than 1. and k is larger than 2 or 3, I mean, it's a constant. So this thing will be smaller than 1. So you want to have the power 2 will be much better than the power 3. So C2 will be always larger than CB. Okay, so this shows that you don't have a super-quadratic quantum speed up here. And we can actually apply quantum search and amplitude amplification on top of this in order to have a square root on the running time, that is dividing the exponent by 2. And this time you get a quantum. So we even get a quantum algorithm which is better than the original one. It's a second conclusion. But the main one is really the theorem 2 that says that there is no super-quadratic quantum speed. Any questions? Okay, so if there's no question, I will try to explain how to get this dequantization. And I will try to do it. I should have 2 or 3 slides. So it's not very complicated. The main thing is to look again at this paper and to do how they do their analysis of the performance of their quantum algorithm, and to try to reinterpret the analysis. Okay. So we are considering MAX-k-CSP with these parameters. So remember that this means that the low energy density condition is satisfied. So which means that there is few low energy assignment. Okay. If you look at all the assignment with a low value here, so where a small enough number of clauses are not satisfied, then these are the assignment depicted in red, and you have a small number of less than 2 to the gamma n for some guy. This is the first thing. We have this condition. A second thing, and the crucial observation, is that we do have the locality. We know that the MAX-k-CSP is a local problem. Okay. So what we can show is that there are relatively many low energy assignments around the optimum. So let's see this picture here. So we have Z star, which is the assignment with the smallest energy, achieving this point. And what we can show is that if you look at around this optimal assignment, you have a fairly large number of assignments with a value, energy smaller than the second threshold. Okay, and we can show that this beta is actually constant when k is constant and mu is also constant. And I will show you this in three lines. But an important thing is that here you have an upper bound and here a lower bound. We will use it in the next one. And another thing, you can think of this gamma being 0.99 and so fairly large constant, and beta being something like 0.01. Okay. So how to prove this? Again, we are assuming that D is constant, which means that the formula is fairly close to being regular. Okay, each variable is involved in a few clauses. So the same, more or less the same number. Each variable is involved in essentially the same number of clauses. So what does it mean? This means that you cannot have one variable such that flipping it will modify all the clauses, the value of all the clauses of the formula. Okay. So from the regularity, we can argue that each variable can only flip a relatively small number of clauses. Okay, so what does it mean is that if you start with Z star and you flip one variable, then you still get an assignment that satisfies a large number of clauses. And the same if you flip 2 or 3 or a small number of clauses. Okay? And by this kind of argument, you can show that all the assignments which are close in Hamming distance from the optimal assignment have a fairly low energy. And this argument is straightforward when the instance is regular, but actually it's also true if it is not regular. You can use another argument to show to reach a similar condition, a similar conclusion. Okay, so we have these two properties. The first property is implied by the condition D and delta. This implies that it will satisfy the low energy density condition. The second one is really the locality of the problem we are considering, and the fact that this one variable cannot impact too many clauses in the case you have some kind of regularity. Okay. So now, look, let's go back to the quantum algorithm analyzed in this paper. It's again the quantum algorithm based on the short path algorithm, which can be interpreted as a quantum adiabatic algorithm, but also in this fairly simple way where you first apply phase estimation and then you do a measurement. And in that paper, the analysis they use some techniques from statistical mechanics. And they also use complicated tools like logarithmic Sobolev inequality in order to show that you do get non-trivial running time, in particular beating n to the n over 2. They do this using these fairly complicated techniques, but we can actually observe that you can do essentially the same analysis based on the two observations I mentioned. The low energy density condition first, and the fact that you have this lower bound of 2 to the epsilon n on the number of assignments in the blue area, where beta is a constant when k is a constant and mu is also a constant. So you can really avoid this fairly complicated argument from statistical mechanics and complicated inequalities and redo the analysis based on two simple observations. And this is what we will use for the dequantization in the next slide. Is there any questions about this? Okay, so if not, I can explain now how to do the same thing, but without quantum. How you can do this purely classical. And the algorithm is very simple. It's one slide. Okay. The first thing is you want to find a Z, a random element, an assignment Z, which value smaller than the first threshold. Okay. So one of the assignment in red here. And you will do it simply using rejection sampling, which is probably the simplest algorithm that you can imagine. You sample a random assignment, you compute UZ. If it satisfies this inequality, you stop. If not, you take another sample Z. And you repeat until you find one Z satisfying this condition. Okay, purely sampling. It's sample, it's called rejections. Okay, and what will be the complexity of this algorithm? So it's of course depend on the number of assignments in the red area. But in the previous slide, we showed that this number was essentially 2 to the gamma n, where gamma was some constant of 0.99 or something like that. And so the number of repetition, the number of samples you need in order to get such a Z will be 2 to the 1 minus gamma n. So for this specific value, it will be 2 to the 0.001. So sorry, 2 to the 0.01 n. Okay, so you repeat until you find such a Z. The first step. And the second step is essentially, it's even easier. You simply try all the assignments close to what you obtain in the first. Okay, so you start with your Z and you check all the assignments which are the closest to Z. All the assignments which have small Hamming distance from Z. Okay, and of course, this can be done with this complexity. And the key observation is that if the Z you get here, the random Z you took, is in the blue area here, okay, since Z star, the optimal assignment, is very close, you will find it. You will find your optimal solution. Okay? And the probability that this happen is a probability that at step 1, you get 1 Z in the blue zone, which is exactly this. We know that at step 1, you do get an assignment in the red region here, so lower than the threshold. And under these conditions, the probability that you do get an assignment in the blue zone here is this. Okay. And then you repeat the whole process, step 1 and step 2, until you find this Z star. And the total complexity, so you need to repeat this number of times. Okay, so the inverse of this fraction. And the total complexity is the number of iterations multiplied by the time for each iteration, which is this plus this. And if you do the math, you get this inequality, this equality. And gamma is this thing, beta is this thing, so you will get, in this specific case, 2 to the 0.99 n. So you get something which is much better than 2 to the n. Okay, so this gives you a completely non-trivial strategy to solve the problem. And the idea is very simple. It's only, you take a random element with low enough energy, and then you try all the assignment close to that one. And you repeat the whole thing. And this works because we know that the number of assignments in the red area is not too high. And we know that there are many actually assignments which are in the blue area, close to the optimal one. So these two properties, which were the key property used in the previous slide to analyze the running time of the quantum algorithms, are also the properties that enables us to design and analyze this classical algorithm. This is the end of the classical algorithm. Are there any questions? Okay, so if not, I will go back to the slide about the results. So what we have shown again is a classical algorithm that solves the same problem as a quantum algorithm, but with a constant value here, C2, which is actually better, larger. Okay, so this refutes the super-quadratic quantum speedup claim from the original paper. And again, if we apply quantum search or amplitude amplification on top of that, you also get a quantum algorithm, which has complexity better than the first. And the main thing is, again, when that C is constant, I mean, well, you should have maybe written C2 here. C2 will be constant for mainly regular instances. And when, for the case, delta constant. Okay, remember, delta represent the fraction of clauses satisfied by the optimal assignment. And the point is that we do get a very simple, but apparently completely new algorithm for MAX-k-CSP. It wasn't known, apparently, before our work, how to get such kind of running time for such kind of instances. Very surprising because it's the algorithm is very simple, but apparently it was completely new. And the nice thing is that in some sense, quantum inspired. We are not directly dequantizing a quantum technique, but the idea behind the classical algorithm really rely on the same idea used to analyze the complexity of this short path quantum algorithm. And yes, from the point of view of theoretical computer science, it's a little bit surprising because it suggested that the case delta very small is harder than the case delta large. Because for delta large, you can do better than 2 to the n using our algorithm, where we don't know how to do it with delta small. Okay. And delta large might be, I mean, intuitively, it seems a little bit harder because you have to satisfy many instances, many clauses, while when delta is small, you are okay with satisfying only a few additional clauses, additional to the value of a random assignment. It's a little bit surprising. And so to finish, so our results show that current short path quantum algorithms do not achieve a super quadratic advantage. And so it's a negative, in some sense, a negative result. But on the positive side, this gives a new quantum-inspired approach to design classical algorithms for important classes of constraint-satisfying problems. And as open problem, maybe one of the most important one, at least from the perspective of quantum computing, is to see if there is a problem or setting for which we can still get a quantum advantage, super quadratic advantage, using this short path quantum algorithm. The second thing, of course, it will be interesting to see how much we can further improve our classical algorithm. And more broadly, we can think about how to design further quantum-inspired algorithm for classical optimization problems. Okay, so I will stop here.